Hey, hello, good morning. Can you hear me? If you can hear me, can someone? Oh, okay, I see some thumbs up. Okay, good. Okay, so it's already 11. I think I will start. Okay, then those that come later will just come along the way lah. Okay, so mainly I think today what we are going to do, because I think Zenden, because of COVID, he missed like I think close to like 4 lessons, and actually he missed quite a bit of stuff. So I went to look through what we did. I think for Zenden, so last Tuesday we actually did a practical. Okay, I teach them how to do the graphs. Okay, and then after that we also did one more practical to practice and how to do your own table and kind of stuff. So this one I'll catch up with you separately. Then also on Wednesday, we started on topic of forces. Okay, so the topic of forces, actually there's quite a few parts to it. The main part that I think yesterday when I was returning the workshop was the vector diagrams. So this one also go through review separately. Okay, so today my focus is just for the rest of this lah. So 3.3 is about Newton's laws of motion. Then but I put this as the last one, okay, because I want to go through. I lay all the basics first, then we come to Newton's laws of motion. You know, all your basics are there, and it will make sense. Okay, so without further ado, I will just begin. So today I'll mainly cover this part. So the 3.1 actually is just introduction lah, like what are forces. So I think set 1 we got learned before. You know, a force is a push or a pull. Okay, that one object exerts on another, and the SI unit is Newton. Okay, so a force can produce, slow down, speed up, stop motion. You can also change the direction of motion. So forces are mainly classified into 2 types: contact forces and non-contact forces. Meaning these forces over here, like your normal reaction force, friction, and tension, you need to be in contact. Objects need to be touching each other for it to be able to act lah. Whereas for non-contact forces, you know, like for example, gravitational force, electric force, magnetic force, realize that like for magnets, for gravity, you know, even if you are not in contact, okay, these forces can still act. Okay, like for example, when 2 magnets repel each other, you don't need to be in contact. For example, you are attracted to the Earth, okay, the gravitational force. Even if let's say you are floating in mid-air, you are also still experiencing gravitational field strength, gravitational force, okay, even though you are not in contact with the Earth. Okay, so yeah, the SI unit is Newtons. So what are some of the examples of forces? So like weight is the gravitational force. Normal reaction force is the one that when you touch the bottom, there will be a normal reaction force. We'll come to that again, okay, in Newton's third law. Force of engine is, you know, the forward force, and friction is, you know, the contact force that, you know, when you push forward, there will be some form of friction. And air resistance is like also like friction, but it's like the air that's pushing against you. So these are the types of forces that common forces that you will see. Okay, so I will skip vector diagrams. Okay, and we will come to friction. Okay, so at friction, okay, so friction, the key concept I want to learn of friction is that, you know, if you ask our question, okay, is friction something good or bad? To some people, the first thing to think of is, oh, friction is something bad. Okay, because we always hear about it, you know, being not a desirable thing. But over here, we're going to learn that actually friction is also useful, and it's very important, you know, in some of the things that we do day to day. Without friction, certain things cannot happen. So we're going to learn both sides, okay, you know, what is the positive or the beneficial usage of friction, and what are some of the, you know, not so desirable usage of friction. How can we reduce them? Okay. So yeah, friction is the contact force. Like we say, it's contact force, meaning you need to be in contact, okay, for it to oppose or, you know, or tends to oppose, okay, motion between surfaces in contact. And it's a result of irregularities in surface, like it's not perfectly smooth. So, you know, there are positive and negative effects of friction, like I said. Okay, so moving vehicles are able to slow down when needed. Okay, if there's no friction, you know, you go on the vehicle, you cannot brake, you cannot slow down. But then also about moving parts in the engines, they suffer wear and tear because of friction, and they need to be replaced. Okay, so yeah, to understand the concept of friction, okay, so this is a very important concept in the sense that it's not very intuitive. Okay, that, you know, friction of acts in the opposite direction. Okay, so in the sense that, okay, so you can see over here, if let's say I have a leg, okay, if how do you actually walk forward is that you use your leg, you dig your leg backwards, correct? You push backwards, and the friction actually acts in the opposite direction on you and actually pushes forward. So that's why when you push, you pull your leg backwards, you can move forward. Okay, so similar to a wheel of a car, when the wheel actually rotates this way, what happens is there's a frictional force that is the opposite direction. So take note, the key concept of friction is in the opposite direction. Okay. So how can we reduce negative effects of friction? So one of the things about friction is, the contact area, the larger the contact area, there's more friction. Okay, so we can reduce the friction by reducing the amount of area in contact. And by doing that, you can do using wheels and ball bearings. Okay, so wheels, I think you know what is wheels now. Okay, so it allows reduces the area of contact surface. So less friction, smaller force needed to, let's say, roll something across. Okay, a ball bearing is actually function like a wheel, but wheels usually only operate in one plane, whereas ball bearings can operate in all directions. You can imagine ball bearings like a wheel, but in all directions. Okay, and ball bearings, because it can operate in all directions, usually there will be, there's some kind of track to make sure that it can roll in a certain direction that you want. Okay, so yeah, but the main thing is also same thing. Because of ball bearings, it can reduce the amount of area in contact, and that reduces your friction. So other than using wheels and ball bearings, other ways that can reduce negative effects of friction, okay, is for example using lubricants, okay, and to polish your surface to reduce the irregularities. Okay, so when it's smoother, there will be lesser friction. So when it comes to answering questions, okay, in your textbook or your workbook, when they say that some surface is smooth, this will imply that there's no friction. Or when they say something is rough, this means that there's friction. Okay, so that's how during the exam, the question they ask you, how do you know whether there's friction in the story that they're telling you? Okay, they say it's a smooth surface means that there's no friction. Okay. So next, air cushion. Okay, so air cushion, how does air cushion work? It basically creates a layer of air between the surface to reduce friction. Okay, so for example, a hovercraft, I think if you are looking at a textbook, page 62, I think there's a picture of a hovercraft. Basically, it's a craft that, that is it's on top of water, but to make it travel faster, it blows some air, okay, between itself and the water, creates a layer of air. So it kind of float on top of the water. This will reduce whatever form of friction there is, and it can move faster. Okay, so one of the main applications that I've seen this before, which actually that day I shared in class, is if you go to arcades, okay, there's air hockey, correct? You realize that air hockey, when they turn off or like when your game is over, you realize that how come the circular disc does not move as much anymore? It will just be stuck. Like you hit it, it doesn't really move. But when you put in the credit, the coin or whatever, and then it starts to be able to float and can like move around very quickly. Okay, and if you notice very carefully your arcade, there's quite a lot of holes on the air hockey table. So those holes, actually what they're trying to create is they're trying to create a layer of air cushion. They keep blowing air out. So next time you go to the arcade at the air hockey area, you can see when you start the game, you can feel that the holes are actually blowing air out. They blow a layer of air. This layer of air reduces the friction between the puck or the circular disc and the surface. Okay, so it floats on top of it, kind of like the air is pushing it out and keeps it afloat. Okay, and then that reduces the friction. So when you hit the circular disc, it can move very quickly across the air hockey. Okay. So in terms of positive effects of friction, sometimes how do we want to create more friction? Okay, for example, for your tires, okay, even for your shoes, you realize that your tires and shoes are not fully smooth and flat. Okay, we actually try to create many grooves, and we call it treads. Okay, the lines that you see, we call them treads. Okay, so these actually create some pattern and it allows a better grip. Okay, and to have more friction. That's why your shoes, after you wear and tear, it becomes very smooth. They become very dangerous. So so similar to your tires, also the car tires. Okay, the wheels. Okay, they also want to have the treads. Okay, to have more friction. Okay. Air resistance is actually a kind of friction. Usually we discuss them a bit separately, but here is using as an example to allow someone to slow down when they are jumping off a plane. Okay, then for rock climbers, I've found this photo over here. I think if you have done rock climbing before, notice that those rock climbers, they always their hands look a bit powdery, a bit white. Okay, because actually what they use some chalk. Okay, it helps to absorb the sweat and also help to improve the grip. Okay, when they are climbing. Because if their hands become very sweaty and all this, it is of course more dangerous because they might slip when they climb. Okay, so basically friction, we only discussed about the bad, the good, how can we reduce the bad and how can we increase the good. Okay, next, free body diagrams. Okay, what is free body diagram? Free body diagram is just a diagram which we draw, okay, to allow us to indicate all the forces acting on the object. Key thing is it must be acting on the object, not forces acting by the object. Okay, I think yesterday we did highlight that when we discussed some of the workbook questions. Okay, so when we're looking at these forces acting on the object. So for example, some of the examples are like your weight, okay, air resistance, the force of engine, the tension, and all this. So all these are forces acting on the object. So free body diagram, the key thing about this diagram is it is not to scale, meaning you are just doing like kind of a sketch to allow you to take into account, what are the forces. So you know that, this object is experiencing all these forces, okay, so that you can use that with your calculations and all this when you're doing your accounting. So it's something not to scale, okay, you don't need to have an exact length, exact angle and all this. Yeah, but just generally. But there are some of the key things to take note, okay, when you are drawing a free body diagram. Okay, one of the first thing is when you are drawing your weight will always draw from the center of the object. Okay, in the next chapter or in the one that is supposed to do in your SRS today, you learn about weights and all this. Yeah, so weight is a force, so it must be drawn from the center of the object. In chapter 5, you'll learn about this concept called the center of gravity. Okay, so yeah, the CG. Okay, so basically we are drawing from CG. So weight should always be drawn from the center. Okay, other than weight drawing from the center, friction should be drawn along the surface. Okay, so maybe we go to an example. Okay, I will skip this. So yeah, we will draw from the center. I think here there's a bit of overlap. You can't see that it's from the center. Okay, another one that you need to think of is for normal reaction force. Normal reaction force is a contact force. So you must always be drawn from the point of contact. In this case, it's between the box and the floor, or in this case, between the car and the ground. Okay, so from this point, okay, then you draw upwards. Okay, so it must always be perpendicular to whatever surface it is on. That's why it's called normal. The word normal means perpendicular. Okay, so this force will be upward perpendicular to the surface. So meaning, if I have the box on the slope, okay, my normal contact force will be like that. Okay, it will not be okay. This one is wrong. Okay, it will be perpendicular to the surface. Okay, and yeah, and you always draw from the point of contact. Okay, so yeah, that's your normal reaction force. So normal reaction force is because what is this normal reaction force? When yesterday I was saying that, let's say you put something on the table, okay, the object will exert a force on the table. The table will exert an equal and opposite force to the object. Okay, so that's where, for example, like let's say why you hit the table. Okay, why is it very painful? Because when you hit the table, while you're exerting a force on the table exerts equal and opposite force on you. That's why you can feel painful. Okay, friction. Okay, friction, take note, it must be drawn along the surface of contact also as a contact force. Okay, so meaning your friction should not be drawn like somewhere from the center of the object. Okay, you will draw along the surface of contact. Okay. So yeah, anyway, for this example, this particular question, they're just saying that, okay, the car is moving to the right, okay, with uniform speed, turn off the engine. So what are the forces acting on it? So it's still moving to the right. So all the forces acting is weight, normal reaction, and okay. So sometimes during exam, they will ask you to draw free body diagrams, or they ask you to label or sketch all of this. Okay, so with that, we are done with free body diagram and friction. So all these like lays out the foundation before it comes to the main part, which is the Newton's laws of motion. At this point, do you have any questions? Everyone all okay? So no questions, Okay, so if no questions, I'm going to move on. Along the way, if you have any questions, you can just let me know. You can drop me a text, or you can type in the, there's no chat room, right? Okay, you can just drop me a text, or you can like unmute yourself or something, okay? So now we move on, okay? Forces and motion, we are going to move to the main part where we learn about the Newton's laws of motion, okay? So first, we start off with the first law of motion, okay? Or before we even start with the first law of motion, okay, we revise on the concept of acceleration. What is acceleration? Acceleration is the change in velocity per unit time. So every time when there's a change in velocity, there will be an acceleration, okay? So applying a force can cause an object to accelerate. So meaning if the object is stationary, it can cause it to start moving. The object is moving, it can either increase its speed, or even change in direction. So all these are considered acceleration. Okay, what happens when acceleration of an object is zero? Okay, does that mean that there's no force acting on the object? So this will bring us to our Newton's first law of motion. Okay, so basically zero acceleration means that the object can be stationary or moving with a constant velocity. Right? Zero acceleration just if you are at rest, you continue to be at rest. If you are moving, you just continue to move in a constant velocity and in a straight line. Because when you change direction, it's considered acceleration also. Okay. This does not mean that there are no forces acting on the object. Instead, it means the resultant or the net force is zero. So this is our Newton's law of motion. So before we continue, okay, what is resultant force? What is net force? Okay, resultant force, net force is basically the sum of all the forces on the object. Okay, so resultant means like the result, the final result. Okay, net or means like you add up every single thing together. So because usually an object, it's not just only one force acting on it, we have multiple forces acting on it. So when you add up all these forces, okay, what is the resultant force? Okay, what is the end product? Okay, so because for example, okay, all these. So let's say I have an object. Okay, I have a force acting to the right, let's say 5 newtons. I have a force acting to the left, 3 newtons. What is the resultant force? The resultant force will be a 2 Newton force to the right. Okay, so it's like because the 3 Newton force will be like countered by this 5 Newton, and overall is as good as you are just having a 2 Newton force acting to the right. Okay. Subsequently, for example, when I go through you vector diagram will actually allow us to find the resultant force, or if let's say the resultant force are not parallel to one another. So for example, let's say I have a force like 5 newtons here, and then another, let's say 4 newtons here. Okay, what is the resultant force? What is the final how will it look like? So like yesterday you might have seen a bit. Okay, we will draw a parallelogram, and then we'll say that it will be somewhere in between. Okay, so and that's how we will find this. Okay, so this one I'll go through with you again. Okay, so with that we move on to the Newton's first law of motion. Okay, what is the Newton's first law of motion? The Newton's first law of motion states that every object will continue in a state of rest or uniform motion in a straight line unless a resultant force acts on it. Yeah, so this basically means that if the resultant force acting on the object is zero, the forces acting on the object are balanced and there is no acceleration. Take a few moments to digest this. Basically, I'm saying that, if resultant force is zero, the object will not accelerate. Okay? If the object will not accelerate, what does this mean? This means that if the object is at rest, it will just remain at rest. Meaning if the object is stationary, it's not moving, it will just continue to stay there. Okay? But if let's say the object is moving, then the object will continue to move at a constant speed in a straight line. You will not change direction, you will not increase its speed or decrease its speed. Okay, so that will happen where the resultant force is zero. And what does resultant force zero means? Does that mean that there are no forces acting on it? No. Okay, it could be there are forces acting on it, but the forces happen to balance out each other. They cancel out each other. For example, you can imagine, let's say I have an object. Okay, I have an object. I have a 5 Newton force pulling to the right. I have a 5 Newton force pulling to the left. What is the resultant force? The resultant force is 0. The 5 Newtons cancel each other. So the object is at rest. What will happen to the object? The object will continue to be at rest. Okay, so it cancel each other. So the resultant is 0. Okay, so that's what Newton's first law is trying to say. It says that, okay, the object will continue to be at rest or in uniform motion in a straight line unless a resultant force exists. Okay, so some examples. So let's say a car is stationary. Are there any forces acting on it? No, resultant force is 0, so it remains stationary. Okay, a car is moving with constant velocity. Are there any horizontal forces on it? Yes. So how does it allow it to continue to move at constant velocity? So there's a forward driving force and your frictional force. How come it can travel at constant velocity, meaning there's no acceleration? This means that the driving force, which is the forward force, must be equal and opposite to the frictional force. And because they are equal, okay, they will cancel each other, and the resultant force on the car will be 0. And the resultant force is 0. This means that the object will travel at constant velocity. Okay, so basically Newton's first law is just that. Okay, next we move on to Newton's. Oh, okay, sorry, haven't yet. Okay, so Newton's first law. So a box is stationary, remains at rest unless it experiences a resultant force. So for example, in this case, why is it at rest? Why is balancing it out? Okay, so you'll be wondering, there's weight pulling on the box, correct? The weight is pulling it down. Okay, then how come the box doesn't go down? Because while the earth is pulling the box downwards, the table is exerting an equal and opposite force on the box. So the box is experiencing one downward force, one upward force. Downward force is by the earth, upward force is by the table. And this weight is equal to the normal reaction force, normal contact force. And because they are equal and opposite, they cancel out the forces acting on the object. The box remains to vertically, there's no change. Okay. So let's say it's moving at a constant speed on a smooth horizontal surface, you just continue, okay, to travel in a straight line at the same speed, unless there's a resultant force. Okay. So next, okay, I don't know whether is any of you on this. You are not online, right? You are just looking, right? Okay. We'll just take a look at the question together. So a boy is pushing a box at constant speed on a straight path. Which statement describes the horizontal force acting on the box correctly? So first thing, when you see constant speed, this will tell you that the box has 0 acceleration. And because the object has 0 acceleration, what does it tell about the resultant force of the box? Okay, the resultant force is 0. And if the resultant force is 0, but the boy is pushing, how does it get a resultant force is 0? This means that the pushing force is equal to the frictional force. Does that make sense to you? Okay, pushing equals to frictional force. So resultant force 0, resultant force 0, no acceleration. You move at a constant speed. Okay, so it cannot be B. Okay, it cannot be C because B says pushing force larger than frictional force. If pushing force larger than frictional force means there's a resultant force, then the object will accelerate. Okay, no horizontal forces. Okay, the boy is pushing, so actually there's forces acting on it. Okay. Another question to just check the understanding. Okay, a hockey puck lies at rest on a perfectly smooth surface. If you give the hockey puck a quick push, okay, a quick push means you only push it. After that, you stop pushing. Okay, the force acts on the hockey puck momentarily, meaning just for a few moments, for the moment you push. After that, there's no more forces acting on it. Okay, it says perfectly smooth. Just now I did mention when they say there's a surface is smooth, we assume that there's no friction. Okay, so after this push, okay, and there's no friction, are there any horizontal forces acting on this part? The answer is no. Okay, because there's no more pushing, no more friction, nothing. So what will happen to the subsequent motion of the hockey puck? Since there's no resultant force or the resultant force is 0, okay, the object will continue to move with constant speed with a straight line. Okay, the speed will not increase because there's no more pushing force and there's no friction. If there's friction, it will decelerate uniformly to rest. Okay, but there's no friction, there's no pushing, so you just continue to move with a constant speed in a straight line. So far, can you understand Newton's first law? Okay, I assume okay. So okay, if you can understand Newton's first law, you realize that Newton's second law seems to be saying the same thing as Newton's first law. It's like the other side of the same coin. So Newton's first law said that if zero resultant force, the object will be no acceleration, correct? Yeah. Newton's second law says that if there's resultant force, then there's acceleration. That's all. Okay. So Newton's second law states that when a resultant force acts on an object, okay, the object will accelerate in the direction of the resultant force. That's all. So the calculation part is that the product of the mass and acceleration of the object gives the resultant force. This one will come to this formula again. So basically, the resultant force acting object is not zero. The forces are unbalanced, there will be acceleration. So first law says resultant force zero, no acceleration. Second law says that resultant force not zero, there will be acceleration. Okay, so let's take a look. If you stay on the accelerator, the car speeds up or it accelerates, okay, meaning it increases the speed. What is happening in terms of forces? Because your driving forward force is larger than the frictional force. So the resultant force is more than zero. This allows the cars to accelerate, okay, in the direction of the resultant force. So, but in the real case, there will be friction. So if a box is given a push that is greater than the friction, okay, the box that acts on the, it becomes unbalanced. So if this push is larger than friction, it will move to the right, okay, and experience a non-zero force, and there will be acceleration. So now if the push is removed, only frictions act on the box. So now the object is moving in the towards the right, so the friction is towards the left. Okay, so what will happen, okay, to this object, okay, because now the resultant force is to the left, this will cause it to so-called accelerate to the left, or actually it means decelerate to the right. So the box is actually moving to the right, but it's decelerating, it's slowing down because the resultant force is on the right. So here brings about a very important understanding. Okay, some people will think that, oh, my object must always travel in the same direction of the resultant force. The answer is no. Okay, the object can be traveling in the opposite direction of the resultant force. Like in this case, the object is going to the right, okay, but the resultant force to the left. This will cause the object to have a, so because based on definition, if we take positive to the right, negative to the left, my resultant force is a negative force, okay, because to the left. Okay, so my acceleration is a negative acceleration, which actually means that it's decelerating. So the object as it moves to the right, it is slowing down. Okay, so that is the non-calculation part of Newton's first and second law. So far, everyone okay? Yeah, so you can see that first and second law, they are just two of the same thing, okay? So basically, first law, no acceleration, no resultant force. Second law, got acceleration, got resultant force. So how do we find out, okay, what is this resultant force and what is this acceleration? Okay, there's one other quantity that ties them together, which is the mass of the object. Okay, so the formula is this: F equals to ma. The resultant force of the object is equals to the mass of the object times the acceleration. Key thing to take note over here, the F represents resultant force. So you can only apply this, okay, with resultant force equals to mass times acceleration. Meaning if this is not the resultant force, like you cannot just say use one of the force and perform this calculation. Your acceleration will not make sense. Unless your resultant force is the only force, like let's say the only force acting on it is friction, and then it's okay. Okay, but if there's more than one force acting on it, you need to add up all these forces, then you get a resultant force, and this will be equals to the mass times the acceleration. So let's look at example. Okay, a car of mass 1,000 kilograms travel on a smooth road at a constant velocity of 50 km per hour. Okay, it experiences an engine force of 5,000 newtons. What is the resultant force that acts on the car? So first thing you need to pick up. Okay, smooth road means no friction. Next, constant velocity. What does constant velocity mean? Constant velocity means that there's no acceleration. If there's no acceleration, what does it tell you about the resultant force? Based on Newton's first law of motion, you should know that the resultant force will be 0. Okay, so you don't need to do any calculation. This is a trick question to see whether you can pick out the concept of constant velocity, meaning no zero acceleration and resultant force 0. Okay, so car travels at constant velocity, not accelerating. So the absence of acceleration means that there's no resultant force acting on the car. Okay, next example, a car of mass 1,000 kg accelerate from rest to 20 meters per second in 5 seconds. So rest means 0 meters per second, okay, in 5 seconds. So if you want to find the acceleration, you can find acceleration by taking the change in velocity divided by the time taken. So the final velocity is 20, initial is 0. So 20 minus 0 divided by over 5 seconds, you get 4 meters per second squared. Okay, calculate the resultant force that acts on the car when the car is traveling on the smooth road. Okay, so now if you want to find the resultant force, so F goes to MA, you know that M is 1,000, A is 4. So the resultant force is 4,000 newtons. Okay, part B, now still the same story, okay, but it's now driving on a rough road, and the rough road exerts a friction of 50 newtons on the car. What is the driving force? Okay, so but just now we already said the resultant force is 4,000. So resultant force is driving force minus frictional force. Okay, because imagine you have a car over here. Oh, actually, that was what I was going to draw. Okay. Okay, how do we get a resultant force? There's your forward driving force and there's your frictional force, correct? So these two forces will add up to give you a resultant force, but because frictional force in the opposite direction of the driving force, it will be negative. I want to find what's the driving force. So if resultant equals to driving minus friction, then driving must be resultant plus friction. Okay, this one is a bit of maths. So driving is equals to resultant plus friction. Resultant we calculated just now is 4,000. They say that friction is about 50 newtons. So you just take 4,000 plus 50, you get 4,050 newtons. Another example, okay, this example was to draw free body diagram first. So they tell you that what are the forces that are on it. There's your engine force, okay, 5,000 newtons to the right. Friction, make sure you draw along the surface. Weight, draw from the center. Normal reaction draws from the bottom, okay, in the center and goes upward. Okay, so this is the free body diagram, labeling all the forces on the object. Okay, you do not need to draw it to scale, you just need to label. Okay, make sure direction is more or less correct. Okay. Then using the free body diagram, calculate the resultant force and the acceleration. Usually the weight and the normal reaction force will balance out each other, so you don't need to account for them. So but the forward force is 5,000, the friction force is 100 newtons. So how do you find the resultant force? You take 5,000 minus 100, you get 4,900 newtons. Okay, so this is the resultant force. If F goes to MA, then A will be equals to F over M. So my F is 4,900 newtons, the resultant force. My mass is 700 kg. Okay, then this gives me 7 meters per second squared. Am I going too fast? If you need me to slow down, let me know, okay? Yeah. Okay, so there is Newton's first two laws. Okay, so recap. What is the Newton's first two law? First law basically says that if there's no resultant force, there's no acceleration. Break it down a little bit more. What is no acceleration? No acceleration means that if it's stationary, it remains stationary. If it's moving, it will just continue to move, but at a constant speed because no acceleration. Okay, then Newton's second law just basically says the same thing, but in the other way. It says that if there is resultant force, then there is acceleration. And what is this acceleration? We find it by taking F equals to ma. So the resultant force equals to the mass times the acceleration. And take note of the concept of the resultant. Okay, resultant basically is just all the forces acting up, like acting together. You add them together, that's your resultant. Okay, so if let's say our resultant force equals to 0, okay, what does that mean? Okay, does that mean that there's no forces acting on it? The answer is no. There can be forces acting on it even though resultant force is 0. It just means that they balance each other out. Okay, so the force equals to backward force or the upward force equals downward force. They balance out each other, resultant force is 0. But there are still forces acting on it. Now we come to Newton's third law of motion. It is kind of different from what I'm talking about in the first and second law. Okay, it says that okay, for every action, there's an equal and opposite reaction. Okay, so basically it tells you that forces always occur in pairs. Each pair is made of an action and a reaction. Okay, key thing, they are equal in magnitude and they are opposite in directions. And one of the most important thing is this. This is the one that guides you whether you can understand what is going on or not. Is the action and reaction acts on different bodies. So far, when we talk from just now until now, when we're talking about forces acting on an object, we're only talking about the forces acting on the object. So usually only talking about one object, for example, the car. What are all the forces acting on the car? Okay, but when it comes to Newton's third law, we need to be very careful in terms of the forces who act on who. Okay, one way to see Newton's third law, okay, you might have heard this also around, is that if A add a force on B, B will add equal and opposite force on A. So they are equal and opposite, okay? Equal and opposite. So meaning if you push against the wall, you exert a force of, let's say, 100 newtons against the wall will exert 100 newtons force on you. So it's equal and opposite. One is you press on the wall is also pressing on you. Okay, so they are on different bodies, A on B, B on A. Let's look at some discussion. Okay, so in this case, like I said, this is actually not Newton's third law. These are not an action-reaction pair. Why? Because both are acting on the box. Okay, weight is the force acting on the box by the earth. Normal contact force or normal reaction force is the force acting on the box by the table. So both forces are acting on the box. So this is not an action-reaction pair. So what are some examples of action-reaction pair? One of them is, for example, just now the weight. Just now I said that the weight is the force the earth acts on the box. Okay, the earth is acting a force on the box, is pulling the box towards itself. So if the earth is pulling the box towards itself, by Newton's third law, it also means that the box is also pulling the earth towards it. So it acts an equal and opposite force on the earth. But then you'll be wondering, how does that make sense? That I don't see the earth moving nearer to the box or what? Right, okay, because what is this force? Okay, let's say the box is, let's say 10 kg. So the weight will be 100 newtons. So if you pull 100 newtons on the box, you can see that maybe the box will move. But then you exert 100 newtons on the earth. Do you think that will make much of a difference? The earth is very huge. Okay, so you will not see, but that does not mean that there isn't. The answer is there is. Okay, so it's equal and opposite. Box on earth, earth on box. This forms an action-reaction pair. Okay. Then, based on that, maybe I go back to here again. What is the action-reaction pair for a normal contact force? The normal contact force, the action-reaction pair will be the box exert a force on the table exert an equal and opposite force on the box. Okay, so the box will exert a force on the table. The table will exert an equal and opposite force on the box. But usually, how do we draw this normal contact force? We will draw it such that it is like that. Sorry. You draw it such that it is like that. Okay, this is your normal contact force, your normal reaction force. Okay, it is acted by the table on the box. So yesterday I also did illustrate a little bit more. Okay, so we noticed that usually the weight, as in this normal contact force, will be equals to the weight of the object, right? You realize that this one is usually equals to the weight, because this is assuming, let's say, the only thing that's pressing it down is the weight. So now, what if on top of the weight, I go and I put my hand on top? I put my hand on top and I also press it down. Then, but will the weight of the box change? The weight of the box will not change. The weight of the box remains the same. But now the normal contact force will increase. Okay, because the amount of force the box is acting on the table will increase. Okay, it will be the weight plus the force I'm pushing down. So the normal contact force will become bigger, such that it will be equals to the sum of these two. Okay, just that usually it's only just the weight, so this rate is equals to the blue. But if I have an extra yellow force, my blue will become bigger. Okay, because now I have the yellow and the red pushing on the table. So the table will push a larger force on the box. With that, that is actually more or less it. Okay, so overall, first law, balance force, resultant force 0. Second law, unbalanced force, resultant force not 0. Okay, so if it's balanced, resultant force 0, it will either be at rest or you'll be moving at constant velocity in a straight line. If it's unbalanced force, it will either accelerate or it will decelerate. Then Newton's third law talk about action-reaction pair. Okay, so F goes to MA actually applies to both, because if my resultant force is 0, so if F is 0, then if 0 equals to MA, M is just the mass, so that cannot be 0. So A must be 0, so that your F, okay, will also be 0. So M times 0 will be 0. Okay, so this means that acceleration is 0 when resultant force is 0. Okay, any questions for me? No? Okay, so if not, that's more or less it for today's portion. Okay, then if you have more questions, do let me know along the way. Okay, then other than that, for Zenden, what else do I need to catch up with you would be, let me see. I will need to catch up with you on vector diagrams. That's all. So, okay, vector diagrams, basically what is vector diagrams? It is just if I have two forces acting on an object, I want to find the resultant force. Just now, all those quite easy, right? Because they are parallel. I can just take one force minus the other, or one force plus the other. I can find the resultant force. So what if the two forces acting on an object are not parallel? How can we find the resultant force? We will use a vector diagram where we draw a diagram to scale, and using the diagram, you can find out what is the resultant force. Okay. If not, that's all from me. Okay. Then y'all can continue, have a good day ahead. Then Zenda, I'll arrange with you another time. Can okay, then bye bye. Bye bye. Thank you. Bye bye.
Thanks, Joe.
Bye bye.
Bye bye.
Bye.
Bye bye.
Huh?
Bye, Uma.
Hi, Mr. Wong.
Any more questions?
I sent to you on WhatsApp
Oh, okay, come.
because like